So I'm going to talk about something that is going back long ways, but I recently discovered that there's still some dispute about it. And I was rather surprised at that, and that's when I started doing the things that I did for this talk. So I shall use the idea of tomographic data collection in general. Cryo-EM is just an example. Uh, any data collection which provides us with approximations of integrals of some parameters, and the parameter is the thing that you want to recover. I don't care what it is. So this is definitely not restricted to Cryo-EM. The idea is that you have some data which provides you with approximations of some integrals of the parameter. The reconstruction is an attempted recovery of the distribution of the parameter from values of such data. Now, there are two major categories of reconstruction techniques. One I refer to as transform methods, and in electron microscopy, the examples are WBP or F filter back projection, and the other is series expansion methods, examples of which are the algebraic reconstruction techniques and SERT. The former methods, the transform methods, are in wide use. They have fast speed and generally simple implementation. The latter methods have been claimed to provide greater detail from incomplete or noisy data. What are they like? The series expansion methods specify the distribution of the parameter as a linear combination of some basis functions. And they estimate the coefficients of such an expansion by some iterative reconstruction algorithm. Iterative reconstruction I will abbreviate by IR. Now, in many fields of application of tomography, for example, in medical CT, IR has become the norm in recent years. I will give you examples of this. This has not happened in cryo-EM. And there seems to be a greater inertia against the use of series expansion methods. And this reluctance by the EM community goes back to 50 years and is still pretty strong, so I found out. So the purpose of this presentation is to discuss this phenomenon. So this may be a talk about the sociology of science rather than science. I will give examples for the efficacy of IR in EM and in other applications. I shall look at the objections to the use of IR in cryo-EM, and I make some comments at the end on the relevance of the topic to current cryo-EM work. So let me first justify this claim I made about that in radiology, iterative methods are pretty standard now. I'll do it by reference to three recent articles, all in the last few months. One was from the American Journal of Neuroradiology, and these are quotes. CT dose was significantly reduced in studies with IR compared with FBP. Signal-to-noise ratio and contrast-to-noise ratios improved twofold with IR. Radiologists graded IR superior to FBP for gray-white matter differentiation and anatomical details. The average reconstruction time by FBP was 101 seconds, and by IR it was 147 seconds, so no change in workflow. I think that's rather important because of, as you will see, one of the objections that have been raised by many people, including myself, against iterative reconstruction methods is that they're slow. But if they properly implemented, then in this commercial computer tomography machines are properly implemented, they work essentially as fast as filter back projection. Another article is from the European Journal of Radiology. And again, I'll give you some quotes. The introduction of IR for clinical CT imaging resulted in many studies evaluating these methods. Overall, the studies showed improved image quality and diagnostic value with IR compared to FBP. Radiation dose can be reduced with IR by 23 to 76% without compromising on image quality. And compared to conventional FBP, IR allows integrating prior knowledge into the reconstruction process. I will give example of this later. Quote from the third, is it the third? Yeah. Next paper, anyway. It said this study evaluates the physical image quality obtained by a commercially available image-based iterative reconstruction system as compared to that obtained by FBP and an iterative reconstruction which is not image-based. I won't get into what is an image-based iterative reconstruction, but it's commercially available in some CT scanners. And the conclusion of that report was that IR uniformly improved the touch-based image quality of FBP over the entire frequency range. Sorry, image-based IR uniformly improved the touch-based image quality of FBP over the entire frequency range, whereas IR improved the characteristic over medium to high frequency. So let's talk about one iterative reconstruction technique. So the whole thing is not absolutely abstract, namely the algebraic reconstruction technique, ART, which is really a quintessential IR approach. ART was introduced in 1970. As I said, this goes back a long way. In an article in the Journal of Theoretical Biology. And I quote from the abstract of that article, we give a new method for direct reconstruction of three-dimensional objects from a few electron micrographs taken at angles which need not exceed a range of 60 degrees. The method works for totally asymmetric objects and requires little computer time or storage. It is also applicable to X-ray photography and may greatly reduce the exposure compared to current methods of body section radiography. What the phrase X-ray photography in that abstract is what is now called X-ray CT. This article was before the first X-ray CT scanner came out, so that was not a phrase that people used. In fact, the first commercial CT scanner was displayed at the 1972 Chicago meeting of the Radiological Society of North America. It used ART for the reconstruction from its tomographic X-ray data. And it's been reported, I wasn't there, but it's been reported that the accompanying lecture received a standing ovation at the meeting, which is not really surprising because you had all these neuroradiologists who for the first time could see what is going on inside the skull. On the other hand, the reception of the 1970 ART paper by the electron microscopy community was quite negative. In the article, Art and Science are conditions for three-dimensional reconstruction from electron microscope images, Crowther and Klug stated that the ART paper made, quote, extravagant and misleading claims. Such a belief, in spite of the currently 2,695 Google citations, Um, this morning when I looked, it was 2,697. So to the 1970 art paper testifying its efficacy in many fields still lingers in the EM community. So what are the considerations for electron microscopists for choosing an algorithm? So my co-authors and I talked to a number of people, and this is our report that the three determining factors are the quality of the resulting reconstructions, the time that the algorithm takes to produce the reconstructions, and the parameters that need to be specified for the algorithm. So in this talk, I will present and critically examine reasons why many electron microscopists rather use WBP than iterative reconstruction. Briefly stated, the underlying claims are WBP is good enough. That is, having an IR reconstruction available doesn't help a structural biologist to reach more accurate conclusions than what could be reached based on WP reconstructions. The second is to do with time, that users like having results as soon as possible so that they can examine their reconstructions. In a typical environment in which reconstructions algorithms are applied, IR tends to require much more time than WBP. For example, it is reported, but it was me, in my book on the fundamentals of computerized tomography from 2009, that the IR algorithm that produces the best quality reconstructions took approximately 20 times longer than FBP applied to the same data. So if you just go ahead and you have a desktop computer and program IR and FBP, the chances are that the IR that comes out will be significantly slower. The same thing was reported in a number of practical environments by a survey paper by Pensek in 2010. And the third negative statement about the IR algorithms is that users do not like having to play with values of algorithmic parameters. They prefer to work with given default values. Pensek also points out in that survey paper, which I just mentioned, that IR algorithms, quote, require adjustments of numerous parameters whose values are not known in advance. So let me get into a little bit more detail about these three aspects: quality, time, and parameters. With quality, of course, the basic question is how is it determined? What is quality? A straightforward approach to evaluating the relative quality of images obtained by various reconstruction methods is to show them to expert users and ask them to rank the images in terms of their perceived ability to provide the sought-after information. A serious problem with this approach that it has been repeatedly reported that the actual performance of expert users in analyzing the images does not match their own predictive performance, not somebody else's, their own predictive performance, based on images, got lots, based on looking at the same images. In other words, users, even expert ones, are not good at predicting the relative goodness of their own performance based on images obtained using various reconstruction methods just by examining those images. Many papers on this. One example, which appeared in the American Journal of Neuroradiology, where they were comparing various diagnostic imaging methods presented in a three-dimensional way. And the question was, which one is the best for diagnosing craniosynostosis? And they showed images to experts, and they selected this. Then there was a break of several months, and they showed the images to the same expert and asked them to make a diagnosis rather than just a judgment. And it turned out that what they said is the best is not what the vulnerable things on which they perform best. So that's very dangerous just to decide what method is best by asking people's opinion. There is a whole field of psychophysics to examine in a reliable manner of how good such techniques are. And one fairly well accepted method is statistical hypothesis testing. And that consists of 4 steps. First of all, you generate random samples from a statistically described ensemble of phantoms relevant to the given biological problem, and you use computer to simulate the data collection by an electron microscopy. Then you reconstruct from the data so generated by each of the algorithms. Then you assign a figure of merit to each reconstruction. That is dodgy. You got to make sure that the figure of merit should measure the usefulness of the reconstruction for solving the biological problem. And I will give an example later on. And then finally, you calculate the statistical significance based on the figures of merit of all reconstructions, by which the null hypothesis that the reconstructions are equally helpful, so for solving the problem at hand, can be rejected in favor of an alternative that one of them is better. And such methodologies have been described many places. The book I mentioned previously has a detailed description and examples of it. So here is an example of quality evaluation. This is from virology, and it has to do with trying to design vaccines. There are spikes on the surface of influenza viruses, and the location of these spikes, there are 2 kinds of spikes, HA and NA, and the location of them is useful for designing the vaccine. In a book chapter on the book is Computational Methods for 3-Dimensional Microscopy Reconstruction. There is a discussion of this in some detail, and these 2 images at the bottom come from that chapter. The central slices of 3D reconstructions, art on the left and weighted back projection on the right from the same data. And based on these images, my colleagues who are virologists said, oh yes, I can see in art much better. I can distinguish in the art reconstruction much better between the HA and the NA. But of course, that has the same problem that I've been objecting to, is using experts to decide which algorithm better. But one can go further. Younes Bankarum, who was one of the authors of that book chapter, finished his doctoral dissertation in 2016, and in it he replaced classification based on human observers by a fully computerized classification. So now you have electron microscopy data, and the whole process is computerized. And out of the computerized process comes classified spikes. That here, this is an image from Ben Carum's dissertation, and the things which are colored red are supposed to be HA, and the things which are colored yellow supposed to be NAs. So there's a totally automatic way of classifying the spikes. May not work, but it's automatic. So the question is, do they work? And furthermore, for my talk, more importantly, the question is, can you classify spikes better based on iterative reconstructions than on, say, WBP? So the Ben Carum went through that whole process of statistical hypothesis testing. He generated 30 test phantom of viruses with randomly arranged HA and NA conformations for each, simulated electron tomography data, reconstructed by both ART and WBP, applied his classification algorithm to get classifications. Now, how good is a classification? People who are in the business of classification have a number of measures. One of them is called classification purity. Don't give the precise mathematical definition, but the higher the classification purity is, the better you do. 100% is that you do perfectly well. And he found that the classification purity was 97.48 based on the ART reconstructions, and it was only 83.93 based on the WBP reconstruction. So you misclassified many more spikes when you did your reconstructions using WBP. So then, of course, the question is could this have been some kind of accident due to all the noise that was gone into the process? And the answer is essentially no. One of the things that statistical hypothesis testing does for you is allow you to assign a p-value to the result, which indicates how unlikely is what you have observed to come by accident. And the results in Ben Carum's dissertation was that if the two methods, ART and WBP, were equally good for this purpose, then to observe such a difference as we have observed, or worse, could only happen once out of 10 to the 7 experiments. Okay, so I'm not getting to time, which is good because time is running out. So I want to give some example of how time can be reduced. I mentioned at the beginning how the timing problems. So one example is the paper on model-based iterative reconstruction. The two panels side by side, the one on the left is WBP, and the one on the right is model-based iterative reconstruction. And when people started using model-based iterative reconstructions, they found that it took over orders of magnitude more computation than WBP. But by working on it further, a paper published a way of implementing it called non-uniform parallel supervoxel algorithm, and it used massive parallelization, and it achieved a speed up 1,665. So when you do that kind of thing, the timing becomes comparable. Another example of that, one which I've been working on, is from proton computerized tomography. proton computerized tomography is a way of collecting data so that you can plan proton beam therapy, which is a way of doing cancer treatment. And it is very intensive in data collection, and original algorithms took days and days and days. You want to run this thing in a clinical environment. You don't want the reconstruction to hold up the flow through the department. When you use proton computed tomography, you have pretty well have to do it day after day to make sure that your proton plan is appropriate for the patient at the time. It has been achieved to reconstruct within 11 seconds for clinical data, which is certainly fast enough. Takes longer to put the patient on the table. That was also achieved by parallelization. Okay, let me say a few things about parameters. There are two different situations which occur. There are parameters where we have a long history and good mathematical knowledge. That's my first example there. For example, if you use blobs as the basis functions, there's a literature going back in engineering decades and decades on how to select the blobs well. And really, if you understand the literature, you can do very well indeed. It also makes it possible to incorporate it, the selection in standard softwares, such as XMIP, but you have to be careful. We've got to make sure that whoever did that did it right. On the bottom, I show what happens when you use the parameters based on the article in the Journal of the Optical Society of America A, which I mentioned above. And what is being reconstructed here is a sphere of uniform material, and I'm just showing the central slice. And if you use XMIP parameters, you get the thing on the right, which is not bad, but why not do better? The other thing is that there's a lot of literature in optimizing parameters for various things. Many algorithms exist for that kind of thing. One that we have been using is an algorithm called LOPEX, and we published about it in the Annals of Operations Research. And it is an algorithm which learns. I mean, this is not a hot topic, but the LOPEX goes back a long way, long before people talked about neural networks and such. Random optimization techniques is not a discovery of the last few years. And it's random, and so we can optimally select the parameters quite automatically. So let me just say something relevant to current work in Cryo-EM. Many people currently working Cryo-EM are not aware which reconstruction algorithm they are using. That may very well be the case. People know whether they use Relion or CryoSpark, but they don't actually know the reconstruction algorithm in the flow, generally speaking. and therefore this topic is not on top of their minds. That doesn't mean that it's not worth to use better algorithms. It's practically an orthogonal thing to everything else. If you do all the wonderful things that I heard at this meeting, at the end of it, you have some estimate of integrals. You might as well use a better algorithm. Nothing to be gained by using an inferior one. Let me finish with one more example from non-destructive testing, so to illustrate one of the advantages of using iterative reconstruction algorithms. Too many knobs. This is from non-destructive testing, and X-ray CT is a widespread inspection technique in industrial non-destructive testing. The large size and heavily absorbing objects cause artifacts due to either lack of penetration of the specimen in specific directions or by having data from only a limited angle range of views. Well-known problem in the Cryo-EM. On the other hand, one can use further imaging modalities, for example, optical scanning or ultrasonic testing, and those will provide data which are complementary to CT acquisition. And one can fuse this data and have better reconstruction algorithm by making use of the data from the other modalities. So here is an example, an iterative algorithm referred to as SART in the literature, reconstructed a turbine blade. It's on the left. And then if we incorporated in the iterative algorithm the data from the other modalities, the reconstruction was on the what we got on the right. I think it's beyond argument that that is more useful for deciding whether the turbine blade is as it should be. I better stop, I overrun.